we are in the process of learning the laws of motion, and this is chapter 3, and we have already discussed the first uh, Newton's law, and I will skip the slides that I've already gone through, and will continue my discussion further on the second law as we move in this lecture. Newton's second law is basically summarizing the mathematical form of the force and the experiments that were done to relate the force and acceleration and relate the mass and the acceleration. The summary of the experiments and the definition in one equation is that that has become the fundamental equation for the classical mechanics, and it is saying that the sum of all forces, the vector sum of all forces, this is vector sum of all forces acting on a body which has a mass m, is actually equal to mass times the vector acceleration a. So usually this sum of all forces is the resultant force or the net force. So net force is really proportional to the vector A, and it is really the proportionality constant that is the mass of the body. This equation is the statement of the Newton's second law. We can write it in another form in which the acceleration is equal to all the forces or the sum of all forces or the resultant forces divided by the mass. Then acceleration of the body is the magnitude directly proportional to the resultant force which is acting on body, and it is directly parallel to this force. We also say that this acceleration for a given force is inversely proportional to the mass of the body. The Newton's second law is a vector equation which states that the sum of all vectors of the resultant vector is equal to mass times the acceleration vector. For such vector equation, we can write the three equations as one-dimensional equations. The first is the sum of all components of the force along x direction, which is equal to mass times the acceleration along x direction. The sum of all forces along the y direction is equal to the mass times the acceleration along the y direction. Sum of all forces along z direction is equal to mass times the acceleration in z direction. Here we must keep in view that this is a case for the three-dimensional studies. If we have a two-dimensional system, then only two equations will appear as the component equations or the scalar equations. So basically x, y, and z components of the resultant force are related to x, y, and z component of the acceleration for the mass. So algebraic sum of the x component of all forces, algebraic sum of the y component of all forces, and algebraic sum of all z component of the all forces is acting on the mass, and it is creating these components of acceleration ax, ay, and az. Then we come to know also that mass is basic property or the inherent property of the object, just like an electric charge. Mass is also independent of the object's surrounding, and mass is independent to the method adopted for the measurements. Mass is a scalar quantity, and the standard international units must be used to express it, and standard international units have the mass unit as kilogram. If we look into the dimensions of the mass, then they are the m, and if we look into the dimension of acceleration, they are the length divided by time square, and therefore the dimension of mass times acceleration are mass length divided by time square. And therefore the force dimension is this mass, length, and time square. No matter what the origin of the force is, whether it is gravitational force or electrical force or a nuclear force, no matter how complicated the equations are which are describing the nature of the force, The dimensions of a force will remain the same, mass times the length divided by the time square. In standard international units, the acceleration is expressed as 1 meter per second square, and the mass is expressed as 1 kilogram. Uh, uh, Therefore, the force is 1 kilogram multiplied by the meters per second square. The combined unit for this force in SI is Newton, abbreviated as capital N. 1 N is equal to 1 kilogram times mass per second square. In CGS system, mass is measured in grams, acceleration is measured in centimeters per second square, so force in this unit system is dyne. It is equal to the gram centimeter per second square, and kilogram is 10 to the power 3 grams, and 1 meter per second square is 100 centimeters per second square. So Newton is 10 to the power 5 dynes. We must remain vigilant when we are using the force and the other ideas of physics, that we should remain consistent with the units. We should use one system of units, and standard international system is relatively simple. Now, if we want to do the dynamic analysis, we want to apply the Newton's second law, then there are several steps that we should always follow. First is that we choose a suitable inertial frame. Remember, inertial frame is a frame which is either at rest or is in uniform velocity or in a uniform motion with a constant velocity. We also select the orientation and the positive direction of the coordinate system such that the reference frame is explicitly expressed. In right direction it is positive, and in a negative direction it is negative, or in a top vertical up north is positive and the south downward is negative. In this manner, we must tell the directions and the positive and negative for the force components. Each object in the problem is there. We will draw a free body diagram which will show all the forces acting on that body, and the body is going to be regarded as a particle in that diagram, not a large cluster or a large thing. It will be a without a structure, a particle. We will label each force with the two scripts. The first will indicate the body on which the force is acting, and the second will be indicating the body in the environment which is causing the force. For example, we will label each force with the subscript for F. Subscript A and B indicates that force on a body A is due to B, and force FBA is indicating that the force on a body B is due to body A. If there are several objects in the problem, then the force on body A will be like this: the force on a body A due to B, force on a body A due to C, and so on. For each body, we find a vector sum of all forces. In practice, this is usually meaning that we have to add separately, and we'll give proper attention to signs for the x and y and z components of the force. We will find the components and separately do the algebraic summation for each component. Then we will use the laws of physics or laws of motion or the Newton's laws to find acceleration components of the body, and then we will do the further required velocities or the times or the displacements. Let us do example. This is a sample problem in which a worker W is pushing a load sled S whose mass M is 240 kilogram for a distance D of 2.3 meters over a surface of a frozen lake. The sled moves with a negligible friction on ice, and so we can ignore the friction. worker exerts a constant horizontal force FSW, which means the force on the sled due to the worker of 130 Newton or 29 pounds as she does so. If sled starts from rest, what will be the final velocity? We are asked. How to solve this? You can see I have made a free body diagram in which mass is shown as a point, a bit circular point without structure, a mass, and a force F SW is going in the direction of positive x. The coordinate system has been drawn, and that's it. There is only one force. So we are taking the force in an increasing direction of x, which is towards right, and we are treating sled as a particle. Now, this is a figure which is called the partial free body diagram because it does not contain the vertical forces, and we have ignored. And we are also saying there is negligible friction, so we are not showing it. So remember, when we want to draw all forces acting on a body, that becomes a free body diagram. This is a partial because only horizontal forces are shown. Here we have omitted vertical forces, and we think that it is not really those forces that are affecting our solution. Then we assume that the force F on sledge by the worker is only horizontal force. Therefore, sum of all forces along the x direction is basically that force F SW. Once we have defined this, we move further. We can find out the acceleration of the sled from the Newton's law. The Newton law says that the net force, or the sum of all forces, is equal to mass times the acceleration. And acceleration along this is, since it is all about the x direction, so acceleration is the sum of all forces in x direction divided by mass. But sum of all forces is the FSW, and then it is divided by mass, and therefore we have the answer. 130 Newton is the applied force, and 240 kilogram is the mass. So acceleration is 0.54 meters per second. With this acceleration, we can find the time necessary to move the distance d, which is needed. The time we want to know because we want to reach at the final velocity. Using the kinematic equation of the type where the distance was involved, we write, let me read it first, that this is x, the position at time t, and x0 is the position at time t is equal to 0. V0 x is the velocity at time t is equal to 0, and t is the time. A is acceleration, ax is the acceleration in x direction, t square is the time squared divided by 2. Now we can write this x0 to be taken to the other side as x minus x0 to be the distance. And this is the distance d traveled by the sled when force is applied. We want to find out how much time was taken to travel this distance. So we solve this equation, and we know that initially the sled was at rest. So we solve this. When we substitute this as a d and this is equal to 0, then axt square by 2 is left. And from this equation, we find out that t is equal to the under root of 2 times d divided by ax. Now we know the value of d, we know the value of acceleration because we have calculated it, and simply we substitute and the answer is 2.9 seconds the time. Once we know the time, then we substitute the time value into this kinematic equation, where the v final is the final velocity equal to vi, the initial velocity, plus acceleration times t, acceleration along the x-axis. Since we know that in this problem the initial velocity was 0. Therefore, the final velocity is just ax times t. Ax is the acceleration along x-axis, and we have calculated it to be the 0.54 meters per second square. T is the time which we have calculated 2.9 seconds. Therefore, the final velocity is 1.6 meters per second, and this is the velocity in positive x direction. The force, the acceleration, the displacement, and the final velocity of the sled are all positive, and it means that they are all pointing to the right of this origin and in this figure. So one can safely say that it is going in the east direction. Sample problem has shown us two important things. The first thing is that if we know the applied force, we can find out the acceleration. Once we have found the acceleration, we can further find out the displacement. We can further find out the time required to do the displacement and the final velocities. Therefore, the position, the final velocities, the time taken, and also the other parameters about the motion can be calculated. So kinematic equations can be employed to do this. However, in this regard, we must keep in view that we are using the Newton's second law as a basis for the uh, acceleration from the net force. Let's do another example, and in this sample problem, we want to reverse the direction of the velocity of the sled in 4.5 seconds. What will be the constant force that must be pushed on sled to do so? We have seen that the sled in a previous example, let me show you, we have seen it that the final velocity was a positive 1.6 meters per second. So it is going in this positive x direction, and we want to now reverse the direction. In the second problem, we want to reverse the direction. So F prime must be applied on sledge by the worker to do this. How much is the question is what will be the constant force? So what are we are given? We are given with the time. The time in this case is known, and we also know the velocity that was here. It was plus 1.6 meters per second. Now the final velocity we would like to see is the negative of it, because we want to reverse the direction of velocity, not the magnitude. So minus 1.6 meters per second, we want the final velocity. So we use the kinematic equation. The V final equal to V initial, the velocity final is equal to the initial velocity plus acceleration along x-axis times t. We have to find out acceleration, therefore the V final minus V initial divided by t is the acceleration. The final velocity must be minus 1.6. The initial velocity was the plus 1.6. Taking the difference of these two, divide it with the 4.5 seconds that are given to us in this much time, then the acceleration is minus 0.71 meters per second square. The magnitude of this acceleration is larger as compared to the value what we have used in problem 3.1, which is 0.54 meters per second square, because now the worker wants to push hard to reverse the direction. So once this force, and we see this acceleration is in the negative direction of x, which is in the decreasing x. Then we also see that the application of the Newton's law is that we want to find out the constant force F dash SW. This is mass times acceleration, and mass is 240 kilograms, and the acceleration is minus 0.71 meters per second square. Therefore, the answer is 170 newtons with the minus sign. Again, the force shows that the worker is pushing the sled in the direction of decreasing x from right to the left direction. So the free body diagram is showing this, that the mass has this force applied in this direction, the negative x direction. So that's how we solve the problem. Here the problem was showing us the final velocity, and we were given with the initial velocity and the time, and we had to figure out the acceleration, and from acceleration we came to know the force. So there are two ways of approaching a problem in the dynamics. One is that we are given with the force or the net forces or the resultant forces or many forces, from where we find out the resultant force. From resultant force, we go further to find out the acceleration, and from acceleration, we find out velocities, displacements, and position and the time. However, if there is a problem in which the other things are given, that is the final velocity, the initial velocity, the time involved, the distances involved, the position vectors, then we go on figuring out the acceleration, the net acceleration, and then net force. But the Newton's second law is applied again. The Newton's third law is really a summary on the force. When a force on a body is acting, you see one body is exerting a force on another body, then the second body is also exerting force on the first one. The two forces are always equal in magnitude and opposite in direction. Here, this is A mass and this is a B mass, and the body B is exerting a force on A as FB, and we can see that a body A exerts a force on body B. Then these two forces are related like this. The force on A due to B is equal to the force on B due to A with a minus sign. The negative sign reminds us that the forces acting are in opposite direction, and it is also usual to label the forces um, due to their mutual interaction. The two bodies sometimes are termed as action and reaction forces, and these labels are commonly used, and they are arbitrary. Either force can be called action and the other can be called as a reaction. So Newton's law is also termed as action and reaction are equal and opposite in direction. The third law gives us a shorthand statement of the law that to every action there is an equal and opposite reaction, and this law requires that the reaction force or the reacting force must exist, and it also specifies its magnitude and direction. We must remember that the action and reaction forces always act on different bodies, as the subscripts will tell us. Often you will encounter situations in which two equal forces and opposite forces are acting on the same body, but they are not this. Let's see a few things in which the action and the reactions are written, and let's try to comprehend this. The action is that the force on a book is due to table. So there is a table and book is placed on the table. So force on a book is due to table. The reaction is that the force on a table due to the table. The force on a moon due to earth. And there is a force reaction, force on earth due to moon. The force on electron due to nucleus, and the force on a nucleus due to electron. The force on a baseball by the bat, and the force on a bat by the baseball. Coming to the first, the force on a book due to table, then there is a force on a table due to book. So correction must be made here. it's a reaction. Remember, the bodies involved in action and reaction forces are different. Here, the force on a book is from table. Here, the force on a table is from book. Now, very briefly, we consider a body of mass m that is released from rest near the surface of Earth. Body will fall. It will fall downward. It will have a free fall, and it will have a free fall acceleration. So, if we neglect the other forces that might be acting, such as air resistance or some wind or some drift, if there is no such thing and this atmosphere, the environment is cool and calm, then body will fall downward, free falling. Here, acceleration will be g, and g is a vector whose magnitude g is a free fall acceleration downward towards the earth. Its direction is vertically downward towards the center of the earth, and that's how the vector g works. Assuming that the earth's surface is a inertial frame, so we can apply the Newton's second law, and the net force on the object is equal to the force equal to m into g. The force is mass times acceleration. So this downward force of Earth's gravity acting on a body is called the weight. So weight is mass times the gravitational acceleration. Force on our body due to Earth's gravity is same, whether it is resting or it is falling or moving. The force has the same magnitude m into g, and its direction is always towards the center of Earth. In terms of magnitudes, the weight is W equal to m into g. So weight of the object must not be confused with the mass. Weight of the object is not mass. Weight of the object is basically a force. It is force, downward force of Earth's gravity acting on a body. So physics makes it very clear that we must not mix the weight of the object with the mass. The gravitational force is the force that causes the weight of the object. This force is directly towards the center of the earth, and it is given by m into g. So magnitude of the weight is m into g. It is the force due to gravity. So if we compare the mass with the weight, remember they are two different quantities. Weight is equal to the magnitude of the gravitational force exerted on the object. Weight will vary with the location. For example, weight on Earth here for 2 kilograms, mass is 2 into 9.8. Weight on a moon is about 3.3. Mass on a Earth is 2 kilograms, and mass on a moon is also 2 kilograms. Although the mass remains same, but the weight is different. Weight is very small. It's about six times smaller on moon. So that's why we say that the moon on moon the astronauts and the other objects feel weightlessness, and their weight decreases, and they keep on hopping instead of walking. Because their weight it becomes low, it is about 6 times lower as compared to the Earth's the weight felt on Earth. Because weight is a feeling of force due to gravity, and the gravity of Earth is different as compared to the gravity of Moon. And let us stop our conversation on gravitational effect on a mass, and move further with the examples and applications of the Newton's second law and the first law and the third law in coming lecture. Thank you so much.